Hi everyone, welcome to the next video for A-level chemistry, and today I'll be going through about enantiomers and how it rotates plane polarized light. So here I've already drawn a pair of enantiomer. So let's label this molecule A, let's label this B. And uh, enantiomers have the same physical properties such as their melting point, boiling points, but they differ when they interact with plane polarized light. So uh so you guys may be wondering what the heck is this? What is the heck is plane polarized light? Okay, this is really ugly written. Let me rewrite polarized. Okay, so I have drawn out a diagram to explain to you guys, and you guys don't have to know how to draw this out for your exam or anything, and this really just for illustration purpose. So when you guys have a light source, let's say a light bulb, right? The light will travel in all direction. Oh, travel in like all direction. Yeah. So when the light pass through this thing called the polarizer, so the polarizer will polarize it. I won't go into the details of how it happens, but after the light source pass through the polarizer, the light will only oscillate in one plane, so it only oscillate up and down. And then this light source will pass through a sample. So let me use a highlighter, a sample solution. And then this sample solution, this contain your enantiomers. And then let's say this is your original light that oscillates up and down. After it passes through the sample, it will get rotated to something like this. It can rotate either right and left, clockwise or counterclockwise, and is rotated by a certain degree of theta. And then after it's rotated, we can choose Z that. After it is rotated, you hit the analyzer, and the analyzer will be able to detect like what's the theta, like how many degrees has a light source has been rotated. Okay, so different molecule has different optical rotation, yeah, standard rotation, and uh, for a pair of enantiomers, they rotate light source in opposite direction, but in equal magnitude. So let's say for A will rotate. If A rotate clockwise, then B will be counterclockwise. And usually for rotation, we assign a positive or negative to show that they are rotating in different directions. And they rotate in equal magnitude. So let's say I have a pure sample of A. Let's say I have a pure sample of A. Pure sample of A. Let's say it rotates by 100 degree. Then a pure sample of B will rotate negative 100 degree. So they rotate in opposite di direction, but equal magnitude. Okay, so here is a sample question that I will show you guys later on. And the next thing that I would want to talk to you guys about is a racemic mixture. You write it down. Racemic mixture, or also known as a racemic. So a racemic mixture whereby a racemic mixture is a solution, a mixture whereby you have 50% of A and also 50% of B. So the ratio of each enantiomer of each is 1:1. So when the ratio of each 1:1, the net rotation is 0 degree. So in this case, it is to be conclude that the sample, the mixture, is optically inactive since there's no rotation. Since no rotation. And in A, let's go back up here. So in this pure sample, since a pure sample of A can rotate plane polarized light, A is optically active. So optical activity is also quite a keyword in this topic as well. Okay, so let's go back down. So why is the net rotation 0? So when the ratio, let me scroll it down a bit. When the ratio is 1:1, when ratio is 1:1, both and sorry, I just rewrite. So equal amount of both enantiomers rotate plane polarized light. Okay, this I'm just taking a shortcut here, but it should be polarized here in opposite direction. In opposite direction equally. Hence, rotation cancel out. Thus, no net rotation. So, what it is saying is that 50% of, sorry, let me switch back to my pen. Okay, 50% of A will rotate by plus 50 degree, 50% of B will rotate minus 50 degree, then you get net 0 degree. So 50 degree clockwise minus 50. So first you go 50 degree clockwise, then you go back 50, so you get back to the same starting spot. So that's what prismatic mixture is about. Okay, so now let's go to the question that I have prepared here. Okay, so most of the time, any question that involve calculation for enantiomers, plane polarized light, is usually like this. This is a classic example, and I rarely see anything harder than this. Yeah, and so today we're going through with you guys how to do this. So there are two ways. So the first way is the algebra way. But let's first read the question. So pure rotates, pure sample of A rotates polarized by 100 degree positive for a sample, for example, sorry, of a mixture of A and B enantiomers. The observed is negative. What is the percentage of each in this sample? Okay, so we know that so let's use algebra. Let A, small a, be the percentage of A. Actually, I should use black instead, so I can annotate later. Let B be small b percentage of B. Right. Okay, then now we know that A versus B must be 100 because it's in terms of percentage. We can't have like A versus B equals 70%. So what's the other 30%? So it must be a percentage, right? And then from here, of this paragraph, we know that the observed rotation is 45. This means that we know that, oh, sorry, where's my, whoa. Okay, so from here, if net rotation is negative, right? So we know that they are more B than A because is B is turning it by negative and A is turning it by positive here, as indicated with this plus sign. So if there are more B than A, we can make form of the equation that B minus A is equal to 45 because the observed rotation is minus 45. This means that this also means that this 40 this means that this 45 is caused by extra of B because if there are any A, the positive effect, the plus degree will have been cancelled out by the negative. Okay, so now we can solve for the equation. So we let's say this one is still you add both of them up. Oh, okay, let's go here instead. Let's come go here. So A plus B, you guys get 2B equal to 145, B equal to 72.5. Then I can solve for A, A is 27.5. So you guys know that in the sample, A has 27.5%. And the sample there's 72.5% of B. And this is the first method. So it's the first method. And okay, there's the second method that I'm about to show you guys, I think is easier. Yeah. And you guys don't understand whatever I just did here, it's okay. It's math. But there's an easier way, I feel. So the easier way is you can draw it out. So what do I mean by that? So let's okay, so what I gotta do is to draw a box. Yeah. Let me draw it like matching this square. Yeah, draw out a box like that. Right. Okay. Let me use a different color. How about okay? I've used green. Let's use violet. So you guys know that here is rotated 45 degree, right? And this caused by B. And then how about in this half here? This half here should contain equal amount of B here and also some A here, right? And since since the observed rotation is 45, it means that this whole entire term get cancelled out. Thus, these two should be equal to each other, right? So if B here is already 45%, this portion here should be 100 minus 45, and that's equal to 555, right? So and then you get like 55 divided by 2 is 27.5. So you guys know that A here is 27.5, the B here is 27.5, and then so A is 27.5, B in total is 27.5 plus 45. Yes, you get back the same answer, 72.5%. Yeah, so I hope that it has made clear to you guys that there's an equal amount of all the A here got cancelled by some B. Hence here the net rotation is 0. So net rotation is 0 degree. And all that the rotation that you guys observe is the extra remaining B. So let me just annotate here, remaining B. Remaining B that causes observed rotation. Yeah, so I hope that this second method is easy for you guys to see. And I only realized this second method I realized this method quite late, yeah, into my uh time of doing this doing Enantiomers. Yeah, so most of the time I went by the first method, but this is much easier actually. And before I end off, I just want to precaution you guys about flight rotation. So there's this concept known as internal plane. That's really bad. Just rewrite it. Internal plane of symmetry. So what it means is that uh, a molecule, let me just draw something random like that, and then zoom in a bit. Okay, draw bromine. Here's your hydrogen, bromine, hydrogen. So you can, as you can see from here, these are chiral centers, right? Chiral carbon. So by right, it should be able to rotate polarized light. And it is a chiral molecule. It should be optically inactive. But what happens here is that there's an internal plane of symmetry. So you can see that both sides are reflection of each other. So for such molecule, it is actually optically inactive. So it's optically inactive. Alright, and sometimes the question are not so kind. But the question are not so kind in this case. This case is a simple molecule, but sometimes it can be trickier. So let's say I have something like this. Let me draw the skeletal formula. It's like that, and then I have chlorine here, and then I have hydrogen, and then from here I have okay, let's say here I have chlorine. Sorry. Here I have hydrogen. Here I have chlorine. And then do you guys still have your uh, carbon here? So from one look, right, it looks like they are uh, from one look, on the first look, from a first glance, it looks like it is a chiral molecule, and it is optically inactive. But in fact, it is not. You guys can actually rotate this bond here. Actually, I shouldn't do that. I should highlight. So you guys can rotate this uh, carbon bond. Why so? Because it is a C single C. You guys can rotate around it. But in this case, the ring formation, this ring formation, it restricts bond rotation. Hence, you guys can't rotate it. So if you guys rotate this bond, you guys rotate this bond like in this manner, you guys will get this molecule. Chlorine, hydrogen, chlorine, hydrogen. So the chlorine from the back comes up, hydrogen floating out the plane, goes back into the plane. The CH3 that's going up now is going down. And then from here, you guys can see that there's an internal plane of symmetry. So it's optically inactive. Yeah. So please remember to check for internal plane of symmetry. Yeah. And so that is all today's video. And I hope that this video is helpful to you guys. And please leave any comments down below if you guys have any question. Yeah. So all the best.